Hello everyone, and welcome back. Today we're going to be introducing two different types of distribution functions known as the log normal and the beta PDFs. So recall that y is a normal random variable with the expected value of mu y and a variance of sigma squared y, provided that the probability density function representation of that random variable y is given by this function here. It's also very important to note that the domain of a normal random variable is typically taken to be minus infinity to infinity. So if you have a continuous random variable that cannot take negative values, positive values, 0, or a combination thereof, then using a normal random variable to model that characteristic is probably not going to be, for the most part, appropriate. So what we're going to do is we're going to look at a special transformation of a random variable or a normal random variable and sort of see what that resulting variable is going to be. Now, there's a very important theorem that talks about one special type of transformation of normal random variables, and it's the following theorem. And it says this. So if x1, x2, down to say xn, where n is some finite number, are normal random variables, and we don't mandate that these normal random variables are IID, so they can have different means or different variances and so on. Then, if we consider the random variable x1 plus x2 all the way out to, say, xn, and you can also put some constants in front of those variables too, you'll still get the same result. This will also be a normal random variable. That is, linear combinations of normal random variables will also be normal. So that's very cool. Now, what I'm going to do is we're going to define a new random variable, but instead of the linear combination, we're going to define a new variable x to be equal to the exponential of y. So if you know anything about exponential functions, you should know that exponential functions are never 0 and they're never negative, provided that y is a real valued expression. So if we're defining y to be a normal random variable, then y is always real. That means x is always going to be non-negative and non-zero. So if that is the case, that means the possible values of x can only be positive real numbers. That means if y is normal, then x, defined as this random variable, cannot be a normal random variable. So one can ask, well, if it's not normal, then what is it? So let's just look at a couple properties of this. So one can show that the density function of this new random variable x is going to be equal to 1 divided by x sigma y times the square root of 2 pi e to the minus 1 half the natural log of x minus mu y all over the sigma y, the quantity squared. Now, it's very important to note that sigma y, mu y, and sigma y are referring to the variable that we have exponentiated. Therefore, it's also very important to note that the expected value of this new variable x is not equal to mu y, and the variance of this random variable x is not equal to sigma squared y. So they're going to be equal to something else. So it's very important to note that sigma y and mu y in this expression are just parameters of this newly defined distribution. Also note that these PDFs do share some similarities between the normal and this new distribution. In particular, the only difference between this and the normal is we have x in that leading rational term, and we also have the natural log of x instead of x, where natural log of x is sort of replacing x in the normal random variable. So this distribution is known as the log normal probability density function, and x is known as a log normal random variable. All right, so a log normal random variable. So what is the connection between a log normal and a normal random variable? So if x is log normal, then the following is true. The natural log of x, which, remember how x was defined as the exponential of a normal random variable, and we know that the natural log of e to the y is just going to be equal to y, and y is a normal random variable. So that means the natural log of a log normal random variable will always be a normal random variable, and the exponential of a normal random variable will always be a log normal random variable by definition. So that's pretty much the general connection between log normal random variables and normal random variables. Now let's briefly talk about some theoretical aspects associated to the log normal distribution function, in particular like its mean, its median, its mode, and some of these other things. Now I'm not going to go through the proof of each of them, but if you're a theoretical statistics or theoretical probability person, these exercises might be fun for you. So let's assume we're interested in finding the mean of a log normal probability density function. So remember that by definition is going to be equal to the integral across the domain of the probability density function of x times that probability density function with respect to x. So for our probability density function, the domain is going to be 0 to infinity, and then x times that probability density function. So 1 divided by x times sigma y times the square root of 2 pi e to the minus 1 half times the natural log of x minus mu y divided by sigma y, the quantity squared, dx. Now, if you do know calculus, this cancellation of x definitely is going to be very, very nice. And keep in mind that this result is not going to be mu y. One can actually show, once you go through that nice little calculus problem, that the expected value of a log normal distribution is actually going to be equal to a slightly complicated looking thing. In particular, e to the power mu y plus 1 half sigma y, the quantity squared. So that's going to be the result that you get once you work out that nice little calculus problem. Right? So not very pretty. And also you can find the second moment, and then you can use our nice little relationship, second moment minus mean squared. And eventually you'll find that the variance of a log normal random variable is also not going to be very, very nice, but it's going to be e to the sigma y squared minus 1, and then e to the power 2 mu y plus sigma squared y. Right? So that's the variance, also not very nice, but at least the solution does exist. Now there are some parameters that do have nice relationships, and let's just mention them because we're going to be using them in applications. The median of x, some people write it as mx, or some people write it as med of x. This is actually just going to be equal to e to the power of mu y. Now this relationship is very, very nice. So usually what we want to do if we want to model something via a log normal distribution is we need to estimate these parameters. So what we can do is we can calculate the median of our distribution and solve this equation for mu y. And you can find that our parameter mu y is just going to be equal to the natural log of the median. Keep in mind, since x is a log normal random variable, its values cannot be negative. Therefore, since the values cannot be negative, the median cannot be negative. Therefore, this expression should be defined as long as you're modeling appropriately. The second metric that has a very nice representation is going to be the mode. Some people write it as MO of x. Some people also write it as MODE of x. Either one probably is okay. And the mode representation is going to be e to the mu y minus sigma squared y in the exponent. Now, it's not the nicest of expressions, but we can actually get a nice little representation because we actually already know how to find mu y provided that we know the median of x. Now our goal is to figure out this next parameter sigma y so that we can use it. And calculating the mode, or the most frequent element in our observations, usually is not a difficult thing to calculate. So let's actually solve this equation here for sigma squared y. So a little algebra exploration. So if I take the natural log of both sides, I'm going to have that mu y minus sigma squared y is going to be equal to the natural log of the mode of x. And then what I can do is I can add sigma squared y and subtract the natural log of the mode of x from both sides. And that's going to give me sigma squared y is equal to mu y minus the natural log of the mode of x. And we already know what mu y is. That's the natural log of the median of x. That's going to be the natural log of the median of x minus the natural log of the mode of x, right? And we can use some property of logs to rewrite this as the natural log of the median of x divided by the mode of x. All right. Now, it's very important to know, or maybe you can treat this as an observation, but for the log normal distribution, the median of x is always going to be greater than the mode of x. So that's going to always be true for a log normal distribution. Right? So if the median is not bigger than the mode, then it's not going to be, or it's likely not going to be, a log normal distribution. So going back to this problem, now I can take the square root of that expression. So that means our parameter mu y can be found by doing the natural log of the median of x. And the parameter sigma y can be found by doing the square root of the natural log of the median divided by the mode. And that is how you find the parameters or estimate the parameters of a log normal distribution. Now, for these calculations, you would have to find the median and the mode of that distribution to estimate those parameters. But there's another parameter that sometimes isn't too hard to calculate, and that's the geometric mean. So the geometric mean of x, so usually represented by gamma. So the geometric mean of x. And that's going to be equal to, one can find, actually just e to the mu y. And remember, e to the mu y is actually just equal to the median of x. So what does that mean? So that means if x is log normal, then the geometric mean is equal to the median of x. Now, does this property sound a little bit familiar from before? It should, because remember, if y is normal, then what is equal to the median of y? That's going to be the mean of y. So there is some symmetry to the log normal distribution, although the log normal distribution is slightly skewed to the right. It does have some geometric symmetry associated to it that might not be clear from, for example, the normal additive perspective. But those are some of the important theoretical things that you definitely should know about the log normal distribution. Now let us look at an example. So let us assume that the strands of hair on a person's head are log normally distributed with a median length of 18 centimeters and a modal length of 7 centimeters. Choose a strand of hair at random. What is the probability that its length is between 2 centimeters and 5 centimeters? So firstly, is a log normal distribution really appropriate for measuring the hairs on a person's head? Well, a person cannot have a strand of hair that has negative length, so that checks out. And also, if it has a length of 0, it's not really a strand of hair at all. So from that perception, the log normal distribution might be an appropriate model for the hairs on a person's head. Also note that we are assuming that the median is 18 and the mode is 7. Since the median is bigger than the mode, then that is also another sign that maybe a log normal distribution is a good model for this. So since those two things check out, now we can go ahead and proceed to estimate the probability that it's between 2 and 5 centimeters. So the first thing that we need to do is, from these median and mode values, we can estimate the parameters mu y and sigma y. So we know that the median value of x is equal to 18 centimeters. So that means we can find the parameter mu y to be equal to the natural log of the median, which is going to be equal to the natural log of 18, which is going to be approximately 2.89. So that's our first parameter. Our second parameter is going to come from the mode and the median. So it's given that the mode is equal to 7 centimeters. That means sigma y, remember, is going to be equal to the square root of the natural log of the median divided by the mode of x, which is going to be equal to the square root of the natural log of 18 divided by 7, which is going to come out to approximately 0.97. So those are our two parameters that we need to solve this problem. So if we construct our model, then we're going to have the density function for x is going to be approximately 1 divided by 0.97, so that's our sigma y value, times x times the square root of 2 pi, and then we're going to have e to the minus 1/2, the natural log of x minus mu y, all divided by sigma y squared. So that's the probability density function that, for example, you would input into Desmos so that you could conduct your calculations. So our density function is going to have that particular shape. Remember that the mode is going to be equal to 7, and we want the probability that our strand of hair is in between 2 and 5. So from this geometric picture, we're interested in finding this area here, where this is the distribution of x. So using some integration, we have that the probability that x is between 2 and 5 is just going to be equal to the integral from 2 to 5 of our probability density function, which is going to come out to approximately 0.0819. So the probability that we select a strand of hair from this person's head and it being between 2 and 5 centimeters is approximately 8%. So that's the practical, or one of the practical applications that you could use the log normal distribution for. The next distribution we're going to talk about today is what is referred to as the beta distribution, which has this analytical form. In particular, this leading term is a constant where alpha and beta are going to be rate parameters. So alpha, beta, which should be non-negative, are going to be rate parameters. Sort of like sigma y and mu y for our log normal distribution. So gamma alpha plus beta divided by gamma alpha times gamma beta times, and this is our variable portion, so x to the alpha minus 1 and then 1 minus x to the beta minus 1. And one may ask, well, why do we call this the beta function? The reciprocal of this leading coefficient is actually the reciprocal of, or the reciprocal of the leading coefficient is the beta function. So b, the beta, is sort of where that function gets its name from. So the area under this curve, x to the alpha minus 1 times 1 minus x to the beta minus 1, is not equal to 1, and we want that to be a probability density function. So what's the area under that curve from the domain 0 to 1? That answer is beta of the two rate parameters. Therefore, you divide by that area, and that gives us a PDF. Okay, so that is some basic intuition of what's going on here. So also the domain of a beta random variable or a beta distribution is going to be the closed interval 0 to 1, and that's pretty much what's going on here. Now if you don't know what the gamma function is by now, that's perfectly okay, but remember that the gamma distribution of x is equal to the interval from 0 to infinity of t to the x minus 1 e to the minus t dt, not dx. And as long as x is a natural number, then it's actually equal to x minus 1 factorial. And at least in the Desmos world, you can actually implement the gamma function via equals to x minus 1 factorial. Although in abusive notation, it gets the job done. Right? So that's the beta function. Now let's look at some analytical properties associated to it. One of the very cool things about the beta distribution is that depending on the values of alpha and beta, you can actually get a wide variety of different shapes for that distribution. A particular example is what happens when alpha and beta are both equal to 1. So when alpha and beta are both equal to 1, what happens? So x to the 0 is 1, 1 minus x to the 0 is 1, and we're just going to be left with gamma of 2 divided by gamma of 1 plus 1, and one can show that that's just going to be equal to 1. So f of x is going to be equal to 1 on the interval from 0 to 1. So what distribution is that? Well, we can get a quick sketch of it. So 0 to 1, and it's going to be a horizontal line, right? The area under that is, of course, 1. So that means f of x will be a uniform distribution. So that means the uniform distribution is a special case of the beta distribution, which is pretty interesting. Now we can make things a little interesting by letting alpha and beta be sufficiently small. So if alpha is between 0 and 1, then f of x will have a vertical asymptote at x is equal to 0. And similarly, if beta is between 0 and 1, then f of x will have a vertical asymptote at x is equal to 1. And if both alpha and beta are both between 0 and 1, then you're going to have a vertical asymptote of 0 and 1. So if you look at the distribution, for example, alpha is equal to 0.2 and beta is equal to, say, 0.3, then you're going to have a distribution with vertical asymptotes there and there, and it's going to sort of look sort of like that. Right? A little bit of skewness there, but I'm not sort of focusing on the skewness at this particular time. Right? So vertical asymptotes there, so it sort of looks like a parabola, but a parabola with vertical asymptotes. A very important characteristic is if alpha and beta are equal to each other, then f of x will be symmetric about the line x is equal to 1/2. So if alpha and beta are both equal to, say, 0.3, then that minimum is actually going to be at 1/2, right? But if alpha and beta are between 0 and 1, and one is bigger than the other, then it's going to be slightly skewed either to the left or to the right. Now, in terms of skewness, usually we don't consider skewness from the asymptotic perspective, so we're just going to focus on skewness from the alpha, beta being both greater than 1. So if alpha is bigger than beta and both are bigger than 1, then f of x will be skewed to the left. So if you want at 0 and 1 to have this type of shape, then what type of parameters would you need to make that true? So let alpha be equal to 5 and beta be equal to, say, 4.6 or something like that. That would do. And if beta is bigger than alpha and both are bigger than 1, then f of x will be skewed to the right. So if you want a distribution to look something like that, almost symmetric, but not quite. Let's assume that 1/2 is sort of there, so it's slightly skewed to the right. So beta is equal to 4.2, alpha is equal to 3.9, would make that particular thing true. And if you want it to be symmetric and non-asymptotic on the boundaries, then, for example, if alpha is equal to beta and both are greater than 1, then as we already know, f of x will be symmetric. Right? And depending on what type of values of alpha and beta you choose, you could have, for example, that's definitely not a symmetric distribution. You could have that distribution, you could have that distribution, or you could have it's not really a bell-shaped curve, is it? You could have that distribution or something like that. As long as the area underneath the curve is equal to 1, that's of course always going to be true for a beta distribution, but changing the values of alpha and beta definitely is going to give you some interesting shapes to consider. So you can definitely model several different applications of random variables, but keep in mind, in its original form, the beta distribution is only defined on the interval 0 to 1. So if you want to change that closed and bounded interval both below and above, you would have to perform some algebraic transformations on that function if that's what you desire. Here's a real-world example of where you may want to use the beta distribution to model something. Keep in mind, the domain of a beta distribution is from 0 to 1, so probabilities and proportions are something that you can model with a beta distribution. So let's assume that you're trying to estimate the proportion of a population that likes panda bears. And you have determined that a beta distribution with parameters alpha 7.1 and beta 3.5 is an appropriate model for estimation. So since this is 7.1 bigger than the beta value of 3.5, this is going to be a skewed left distribution. So that means if this is true, that means more people will like panda bears than those that will not, at least in terms of likelihood, if you were to select a simple random sample or individual. So, based upon this model, what is the probability that more than 50% of the population likes panda bears? Is it definitely certain, like 100%, 80%, or is it, like a 50-50 type of thing? So, let's build our model. So, what do we know up to this point? So, we've decided that alpha is equal to 7.1 and beta is equal to 3.5, and there's some definitely different ways that you could estimate these parameters if, for example, this is something you want to construct. So if alpha is 7.1 and beta is 7.5, that means alpha plus beta is going to be equal to 10.6. So that means our distribution f of x is going to be equal to gamma of alpha plus beta divided by gamma of alpha times gamma of beta times x to the alpha minus 1. So alpha minus 1 times 1 minus x to the beta minus 1. So that means our probability density function to estimate the proportion of people who like panda bears in this population is going to be f of x is equal to approximately 494.31 times x to the 7 minus 1 minus 1 is 6.1, and then 1 minus x to the 2.5. Right? So this is going to be the model that we're going to be integrating. So let's just draw our little picture here. So here's 0, here's 1, and here's our skewed right distribution. And we want the probability that x is bigger than 50%. So we want the area of this shaded region and not the area to the left of that. So that means what? So that means the probability that our proportion P is bigger than 50% is going to be equal to the integral from 0.50 to 1.00, or 50% to 100%, of f of x dx, and one can find that that's approximately equal to 0.8778. Right? So therefore, we are 88% sure that more than 50% of our population likes panda bears, right? So that's a very happy thing for panda bears. Right? So that's an application of the beta distribution. Hope you enjoyed, and I'll see you in the next video. Take care.